Google has published papers on distributed systems such as BigTable, Chubby, and the Google file system. During this episode, we focus on a product that takes inspiration from Google's Spanner project, a database that is built on a distributed, monolithic, sorted map. CockroachDB is a scalable, survivable, consistent SQL database. Today's guest, Ben Darnell, is the CTO of Cockroach Labs, and he joins us to discuss SQL and NoSQL and the trade-offs that different types of distributed databases can make. Ben explores these trade-offs between database types and explains how CockroachDB provides many of the best features of both a SQL and a NoSQL distributed database, while also providing the survivability of a cockroach. After a word from our sponsor, we will get to this episode of Software Engineering Daily. As a software engineer, you have tremendous leverage in the employment market. Every company needs software engineers, and these companies are all competing for you, the engineer, a scarce resource. But as an individual engineer, you don't have much insight into this incredibly opaque market. That's where Hired.com comes in. Hired.com assigns you a talent advocate who works to understand your needs and works to find you the perfect job. Go to hired.com/SEDaily to try out the platform today and get a $2,000 bonus if you find a job. The companies on Hired compete for you, the engineer, and they make bids to win your talent. These are companies like Facebook and Uber, companies that we know are on the cutting edge of engineering because they've come on Software Engineering Daily to talk about their tech stack. I've used Hired personally and have experienced firsthand the ease of finding a well-paid, enjoyable job. This was way better than replying to LinkedIn messages from uninformed recruiters, and it was also certainly better than using a job search engine. To find a great job and support Software Engineering Daily, go to hired.com/SEDaily and get a $2,000 bonus upon finding a job. Check it out. It would support the show. Now let's get on with the show. CockroachDB is a scalable, survivable, strongly consistent SQL database. Ben Darnell is the CTO of Cockroach Labs, which makes CockroachDB. Ben, welcome to Software Engineering Daily.
Thanks, Jeff, for having me.
Today's database systems force you to choose between consistency and scalability. Explain why this has historically been a trade-off.
So in a traditional relational database, you have a single database server which can serve strongly consistent transactions because everything is stored in one place. Now, what we saw with the NoSQL movement starting in the mid 2000s was that people would move to a database system like BigTable or its descendants HBase and Cassandra, or a document-oriented database like MongoDB, and this would give you the capabilities to spread your data out across a lot of different machines and let you add lots of capacity cheaply. But it had the downside that these nodes weren't tightly coordinated with each other. And so you would not have strong consistency across the different nodes. And so, for example, it was possible for a record to be updated on one node without a corresponding record on another node to be kept up to date. And so in CockroachDB, we are building a system that is strongly consistent and transactional at every level, and so that the changes that you make across all the nodes, no matter how the data is laid out across the different physical machines, everything is transactional and atomic, and so all the records either update or don't, depending on the state of the transaction.
I'd love to dive a little bit more deeply into this SQL versus NoSQL set of trade-offs before we talk more about CockroachDB. So relational SQL databases have some great features like declarative SQL. They have good support for indexing and transactions, but they have poor horizontal scalability. Why is it difficult to scale a relational database?
So it's difficult to scale because the relational model is so flexible. You can say in a SQL statement, essentially arbitrary transformations on arbitrary amounts of data. And you can see this even in a single node. There's huge differences in performance from one SQL query to another, depending on exactly how the query is written and how the data is laid out on disk and how it's indexed. And so, distributing a relational database is essentially just a much harder version of this already hard problem. And so that's where NoSQL comes in. NoSQL databases specifically give up a lot of that flexibility and power, and then they've reduced the problem to a simpler state that is then easier to solve in a distributed fashion.
So, okay, NoSQL databases, in contrast to SQL, are scalable to large clusters, but there are limitations. You don't have strong transactional semantics, so it's easy for your data to become inconsistent among shards and replicas. Explain this in more detail. Why can NoSQL databases lead to inconsistency?
So first of all, NoSQL databases are a broad category, and so there's so what I'm saying may not apply equally to all of them, but in general, what most NoSQL databases do is they either don't support transactions at all, or they only support transactions in a limited fashion. For example, they only support transactions within a single row in HBase or Cassandra, or a single entity group in some systems. There's usually some unit of distribution that is also the largest scope you can have for a transaction. And so anything that you want to do across transaction, across whatever these units is, across entity groups or whatever they may be in any given system, this has to be this is a non-transactional operation. And so if the database or the client fails at an inopportune time, then the transaction may have, or the operation may have been completed on one node and not on another. And so, for example, if you were building a bank on top of a database, when you want to subtract $50 from account A and add $50 to account B, you have to make sure that both of those things happen, or neither of them do. You don't want to either destroy the money or create it out of thin air. And so that's a big problem for doing certain kinds of things in a distributed database, because the data that you want may not be arranged in such a way that the transactions you want to do are possible.
Most NoSQL systems can only claim eventual consistency. What are the kinds, and for listeners who don't really understand the concept of eventual consistency, we've done many shows about consistency and distributed systems, and there are plenty of episodes you can go back to learn about this, such as a recent episode about React. But assuming our listeners know what eventual consistency is, what are the kinds of applications where eventual consistency is not good enough?
Yeah, so first of all, I want to clarify that eventual consistency is really separate from the question of SQL versus NoSQL, because SQL databases in the typical kinds of replicated configurations that you see when you replicate a MySQL or Postgres database, that these replicated systems are also eventually consistent, because the replication is done asynchronously, and so the update will be made on the master before it is asynchronously replicated to the secondary, and so the eventual consistency is a separate question from whether the database itself is transactional in a single copy. And so back to the question of when is eventual consistency good enough and when is it not? Well, the thing is that eventual consistency is really kind of a marketing term that was come up with by some of these NoSQL systems. It's not really consistent in any strong sense of the term, and so you have
So a more accurate term is usually inconsistent, or
it's not usually inconsistent. So actually, one way to look at it is that an eventually consistent system is not necessarily durable. So if you're familiar with the acronym ACID, describing the properties that you want in a transactional database, that's atomicity, consistency, isolation, and durability. So the last point of that is durability, meaning that once you've committed a transaction, it essentially stays committed, and that's actually the part that is lost with an eventually consistent system, because the data could be lost before it's replicated.
Okay. Well, now that we've had a broad overview of SQL and NoSQL and some consistency discussion, let's get into CockroachDB. What is CockroachDB?
So CockroachDB, as you said at the start of the show, it's a distributed transactional SQL database. And so we can dig into each of those terms one at a time. So it's distributed, meaning it runs across a large number of machines, potentially spanning data centers and large areas. It's transactional, meaning that everything you do is run as a part of a transaction and is consistent and atomic. And that these transactions are also fully distributed, so you can have arbitrary transactions over any subsets of your data. There's no restrictions on what can be a part of a transaction. It's also a SQL database or a relational database. This is the interface that you use to interact with it. This is a work in progress, but we're aiming to be compatible enough with standard SQL that you can use off-the-shelf ORM products like Django or Rails or Hibernate or things like that. And we're not to the point yet where you can just use these things off the shelf and have them work, but we're aiming for that as a compatibility goal. So you're not having to write raw SQL queries or do custom work for CockroachDB. It's something that you can use off the shelf with the same tools that you would use if you were using MySQL or Postgres or anything else.
Before we get into the implementation details of CockroachDB, are there any other design goals, some high-level goals that CockroachDB is trying to achieve?
There are several. One of the other things that we are making a big effort in that I haven't touched on yet is we're trying to be very easy to deploy and operate. This is something that is kind of a necessity when you're running at very large scale on lots of machines, and it's specifically an area that we think is lacking in a lot of the products in this space right now. And so Cockroach is shipped as a single binary with no dependencies. You run this binary on any number of machines. You give each node the addresses of at least one other node in the cluster, or you point it at a load balancer that knows how to find them. And then they talk to each other and sort of self-organize from there. There's no need to statically choose a primary and a secondary, or you don't need a separate zookeeper cluster or anything like that. Everything is self-contained, and once you run this binary on all of your servers, the Cockroach system basically takes it from there and is responsible for migrating data between nodes as necessary, making sure that everything is fully replicated up to your target configurations and so on.
So now let's start talking about the architecture and the implementation of CockroachDB. CockroachDB is architected as a sorted monolithic map. Explain what this means.
Yep. All right. So to explain this, this is actually an architecture that's not that unusual in the database world. A lot of other databases use a similar kind of strategy in a non-distributed way. So what this monolithic map means is that all of the data in your table in your tables is ultimately encoded into an ordered key value store. And so for each record in a SQL table, we construct a key, which is an encoded representation of your primary key, prefixed with the table ID and that sort of thing. And so we have what is conceptually one giant key value store of all of the data in your data, and then indexes are other rows in this key value store that are represented in a different way.
So does each key corresponds to a row in a MySQL database, sort of, or in a SQL database?
Each key in this key value store actually currently corresponds to a column value in a row. Okay. And so at the end of each key, there's a column ID. This is actually something that we may revisit in the future to be able to group multiple columns into one key value to make things go more efficient at the low level encoding. But currently it's stored as a sparse matrix, essentially drawing inspiration from BigTable and Spanner in terms of this design. But so we have the one giant sorted map containing all of the data in the database, and then we take continuous subregions of that map, and we call those ranges, and then those are the physical units of storage and distribution in the system. And so, if you look at it alphabetically, to simplify things a little bit, then we may have a range for all of the records starting with A through C, and then a second range for all the records starting with D through F, and so on. And so we split it up into contiguous ranges, and then those ranges are the unit of distribution. And so each of those ranges is stored on at least 3 different nodes in the system, and the 3 replicas of a range are the ones that coordinate to ensure that all of the changes to that range are done atomically.
Got it. So the just to make sure I've got this correct. So each the map that is distributed across at least three replicas defines a key space, and each key corresponds to a column value of a specific row in a what at a higher level of abstraction is a SQL database. Right. And so if you wanted to have a SQL representation of this, you would have you would conceptually have a SQL table, and each value within a given row has a mapping associated to it. And in order to find the value of that mapping, you would go into the distributed map of CockroachDB. You would look through this distributed range of key spaces, and the key that you're looking up would correspond to the value that you want to load into your SQL representation. Is that correct?
Yeah, that's right.
Okay, very interesting. So the highest level of abstraction is SQL. CockroachDB uses a grammar that is similar to Postgres, and the layer below that is this distributed sorted key value store. How exactly does the SQL layer interface with the key value store layer?
So the key value store exposes an RPC interface that gives you operations like get, put, increment, delete, conditional put, a handful of different primitives, and you submit these as batches into the KV layer. The KV layer can actually then goes to partition these at range boundaries, and so it figures out which operations can be sent together because they fall on the same range, and which need to be separated out. And so we have so there's kind of a first layer of the system, which is, logically speaking, something like a client library that understands the key structure and how to split up the requests and farm them out to the different nodes, and then it sends the nodes out to sends the requests out to the nodes that hold the data, and then those nodes will send the requests down through Raft to ultimately be applied via consensus across all the replicas of the range.
Data is stored across distributed nodes in this distributed this system of ranges. So explain what a node is and what a store is to disambiguate this, and describe how stores are nested within nodes.
Right. So nodes and stores. A node is essentially a Cockroach server process running on a machine. So you will so nodes and machines are generally synonymous. You can run multiple nodes on one machine for testing purposes, but it wouldn't make sense to do that for production use. So a node and a machine are more or less synonymous. And then in practice, you would have one store for each disk on the machine. So in the simple case, you have a bunch of nodes, each with one store. If you have multiple disks per machine that are not organized into a RAID array or something like that, then you would have multiple stores on those nodes.
As a CockroachDB deployment scales, ranges get broken up across nodes. Explain how this range distribution works and how ranges get reconfigured as a deployment grows.
Right. So initially, when a cluster is first deployed, it only contains one range. And so as data is written into the database and that range grows, it eventually hits the maximum target size for a range, which is currently 64 megabytes. And then that's going to trigger a split operation. And so in a split, we look at the data in the range. We pick someplace near the midpoint of that range, and then we do a split and create a second range off. So the range itself, the original range shrinks to cover its left half, and then we create a new range to hold the data from the right half. And so then after this split has occurred, then we now have two ranges that can be moved around and rebalanced independently. And so the nodes all talk to each other using a gossip protocol to essentially broadcast information about how heavily loaded they are, how much free space they have, and so on. And so when a node notices that I've got my disk usage is 10% above the median, then I'm going to try and shed some of this load. I'm going to find a node whose disk usage is below the median and ship them some of my data.
You mentioned the gossip protocol, and you've also mentioned Raft earlier in this conversation, which is another distributed systems protocol. And maybe I'm not great at understanding how these two types of protocols contrast, but I think that something like Raft or Paxos is a little stronger in terms of how frequently it tries to synchronize a system versus a gossip protocol, which is a little more opportunistic. Is that accurate?
Yeah, that's accurate. So Raft is a distributed consensus algorithm, just like Paxos. And it provides very strong consistency and ordering guarantees. And so whenever you make a change to your data, this is actually done through Raft. And Raft essentially runs what's like a mini election for each change that comes through. And so as I've said before, each range is replicated on 3 different nodes, and one of those nodes will be elected leader at any given time. And so any rights to that range go to the leader, and then the leader is going to forward that request to each of the followers, and it's not going to consider the operation complete until it has heard back from a majority of the followers, or a majority of the replica set. And so in most cases, that's 2 out of 3, or it could be 3 out of 5, depending on how your replication is configured.
Yeah. So these two different types of distributed systems protocols, could you give some, for people who are really unfamiliar with distributed systems, or they're trying to learn, give an idea of like when you would use these two types of protocols. Like, why would you use a Raft or Paxos protocol to synchronize stuff more aggressively versus an opportunistic gossip protocol?
Right. So Gossip is very different from Raft. Gossip is a very cheap broadcast protocol essentially, and so it's a good way to get to get data cheaply across the entire cluster, but it provides no consistency guarantees at all, and so. In this case, this is why we use Gossip for things like the disk usage of a server, because it doesn't really matter whether you're basing your rebalancing decisions on the up to the minute disk usage of the server or whether that lags behind by some period of time. And so that basically Gossip is just like Gossip in the real world, it's undirected and kind of not fully controlled, and so when you put something into Gossip, it will eventually make its way across the entire cluster, but there's no strong guarantees of how long that will take. It's not directed to anywhere in particular. Whereas Raft is very tightly controlled. It produces an ordered sequence of operations and guarantees that sequence is complete and identical on every replica.
How similar is CockroachDB to the Spanner database technology designed by Google?
So Spanner is definitely our biggest single inspiration. It's kind of the existence proof that tells us that something like this can be built and work well at scale. I think and a lot of our high level design points are similar. They're both based on monolithic sorted map, for example, and the splitting up. The Spanner is also divides things into what they call spans, we call ranges, and puts these into independent consensus groups. The biggest difference, at least in terms of what is widely known and understood about Spanner, is that Google actually went to great lengths to build atomic clocks for their data centers to provide very accurate time signals for their servers, and that is something that we won't have because Cockroach is designed to run on commodity hardware in whatever data center you may have, and so we can't rely on exotic timekeeping hardware, and so that places certain limitations on the way that our transactions can work. So our transaction model is slightly different from Spanner's. Spanner's transactions, if you're familiar with the concept of isolation levels in SQL, in SQL, you can have transactions that run at different isolation levels, like read committed, repeatable read, serializable. But those are the ones that are typically offered in SQL databases. But that's if you look at the literature in distributed systems design, there are actually a bunch more different isolation levels that are possible, and so Spanner actually provides a very strong guarantee called linearizable, which is an even stronger guarantee than the serializable transactions that are the top level that most relational databases offer. And a lot of that comes from the fact that they have this atomic clock synchronization. For us, we don't have that capability, and so our transactions actually are serializable. So slightly weaker isolation than you would get with Spanner, but still, matching the top tier isolation of other relational databases.
Got it. So we will get into this, and I guess we might as well. A good place to start might be to touch more on this idea of why Google needed to build atomic clocks or atomic clock technology in order to have really accurate timestamping, and that definitely relates to this linearizability feature of Spanner. Even though CockroachDB doesn't implement linearizability, I think it's an interesting topic of conversation as to like why CockroachDB, because it's running on because it wants to run on commodity hardware literally cannot guarantee linearizability. So yeah, let's talk about that a bit. I don't know where the best place to start is, but maybe it's with this term external consistency. What is this term external consistency? How does that relate to the term linearizability? How does that relate to serializability?
I'm not sure of the exact definition of external consistency, so I'm not sure that I can answer that precisely. But
okay, maybe I read too much into the Spanner paper, Spanner paper's vocabulary. I'm just not. This is not my area of expertise in the system, so I'm not. These consistency terms, they're all about marketing.
No, they do make. They're not just marketing. They do have very specific definitions, and so that's why I'm hesitant to go into the parts of the vocabulary that I'm not completely up to speed on. But I can talk a little bit about the difference between serializable and linearizable transactions and how that can come up in practice. And so
yes, please.
Yeah. So first of all, the fact that we don't have atomic clocks doesn't mean that we can't offer linearizability. It means that doing so is much more expensive for us than for Spanner, because with Spanner and atomic clocks, they know that all the clocks in the cluster are synchronized to within I believe 7 milliseconds of each other. And so it turns out that an easy way to provide linearizability is to just insert a 7 millisecond sleep in your transaction at certain places, and then that is enough to guarantee linearizability. Now, for us, without atomic clocks, we have to rely on NTP instead for clock synchronization. And that gives you much looser guarantees. You may have an upper bound of a quarter second or half a second or something like that for your clock synchronization. And so you can be linearizable by performing that sleep, but sleeping for a quarter of a second is a much less attractive proposition than sleeping for 7 milliseconds. And so if you really wanted to run in linearizable mode, that is an option, but it's not. That's something that's a lot less appealing. Anyway, so to explain the difference between serializable and linearizable, the difference is fairly subtle. But the best way to explain it is that in a serializable transaction like Cockroach provides, everything is very strongly consistent between two transactions as long as the two transactions touch at least one key in common. If the two transactions touch at least one key, then that key kind of acts as the coordination point to ensure that one transaction definitively comes either before or after the other. If you have two transactions that don't touch any key in common, then those two transactions can be in a kind of ambiguous state where they commit at almost exactly the same time, and it's hard to tell which one comes before or after. And so this is where linearizability comes in. In linearizability, it is definitely possible to assign an ordering for these two transactions, even though they didn't touch the same keys. In Cockroach, it's possible for three transactions, each of which overlaps with each other, but doesn't. They don't all conflict with each transaction interferes with kind of the neighboring transaction on one key, but not with another transaction. Sorry, I'm not explaining this very well, but you can get into You can get into cases where two transactions are actually kind of ambiguously ordered, where transaction transaction A comes before transaction B, which comes before transaction C. But if you consider A and C in isolation, then there's some ambiguity between them. Yeah. The difference has to do with the ability to define an ordering between transactions that don't touch overlapping keys.
Okay, and so for a listener who doesn't know much about distributed databases, it might have seemed like we've gone from this strange conversation about distributed databases to this conversation about atomic clocks and time, and they just have no idea why we went from one thing to another. And I think the key point to make here is that versioning is really important to these types of databases. And data in Spanner, which is, like you said, is one of the inspirations for CockroachDB, data in Spanner is temporal and versioned. Give an overview of how versioning works, how different versions are stored, and why clocks are so necessary to this.
Right. So earlier when I was talking about the monolithic key value sorted map, I glossed over one detail there, which is that the key for all of these key value pairs, there's actually it's actually not a key value pair, it's a key timestamp value triple. And so each value has a timestamp associated with it. And so that timestamp is assigned when the transaction is written. And so that's why it's so important to have consistent clocks across all of your nodes to make sure that when a new value is written, it has a timestamp that is greater than any other value that was previously written for the same key.
So how many versions of a value are stored at once? Do you just overwrite the previous version, or do you keep track of the past?
Yeah, we keep track of the past. So this is good for read-only transactions, because read-only transactions will have a timestamp assigned when they start, and then they can always read the value that was current at that time, even as other transactions are going on top of them. So this is part of our concurrency model, so that read-only transactions can continue to execute while the data is changing sort of in the future. That they operate at a consistent point in time. And so we keep data around until a garbage collector comes along and deletes the old versions. Currently, that defaults to keeping the old versions for a day. This is something that can be configured, and you may want to either reduce that value to garbage collect things more aggressively if there's a lot of churn and so you're wasting a lot of space on this historical data, or you could increase the value if you want to keep the old data around, so you can query and say, oh, what was the value of this table as it existed yesterday?
Got it. So you touched on some read, stuff that happens during a read, stuff that happens during a write. But I'd like to talk in a little more detail about how a read versus a write works in Spanner or CockroachDB, just to give listeners a better idea of just how the transactionality works. So maybe you could describe a read from top to bottom and a write from top to bottom.
Sure. Yeah, I'm going to start with writes, because that's actually slightly simpler to explain, and the read part won't make sense until you see how it interacts with the data that's being written, because that's where the data that you're going to read comes from. But so in a write, like I said, everything goes through Raft, and so the write always originates on the leader of the range. And then Raft, it submits the proposal to Raft. Raft conducts its little election among the replicas, and then comes out with an ordered list of operations to apply. And so then all three replicas will apply this operation in the same order, and so that's what guarantees that the data stays in sync. And so all writes are fairly straightforward, given the distributed consensus primitives that we're building off of. Reads for reads, it would be possible to do the same thing. You could just send a read into Raft and then get the log entry back out of Raft, and that would give it an order in between. So this would tell you which version of the data you should read, because you know what order the consensus log came out in. But this is pretty expensive. It involves talking to all three replicas, or to a majority of the replicas. These replicas have to write to disk, and that's just way too expensive for a read-only query. Especially when you consider that in real-world systems, reads tend to be far more common than writes, and so we need a more optimized path for reads. And so the way we do that is by granting a lease to the leader of the range to say that leader can serve reads on its own without talking to the other replicas for as long as that lease is valid. The lease is actually managed through Raft itself, so that we know that nothing can happen before or after the lease, or nothing can happen before the lease was granted or after it expires, and all of the nodes agree on that through the order of the Raft log. And so the leader has a lease which allows it to serve these reads directly, and it also is responsible for doing various kinds of bookkeeping to make sure that it won't serve a read that conflicts with a write that it's already proposed, and it won't propose a write that conflicts with a read that it's already served.
So I'm sorry, maybe I missed that. Did you say that when you read, you provide a timestamp, or does it just read based on the timestamp of when the transaction comes in? Or?
Yeah. So at the level of the range, by the time it comes down to the range, the read already has a timestamp assigned to it.
Got it.
Sorry. If the read is a part of a transaction, you can also do a read outside of a transaction that doesn't have a timestamp associated with it, and then it just gets the latest value when it comes through to the leader. But if the read is a part of a transaction, then it will have a timestamp assigned by the time it comes down to the range leader.
And the timestamp is kind of a guard on the level of time-based consistency of that read.
Yeah. So the timestamp is the timestamp is just saying, get me the value that was current at this time, and so. Yes. The reason this is kind of complicated is because writes take some time to come through, and so say you get a write coming in at time t1, so the write gets proposed, it's kind of stuck in the process of going through Raft, and then you get a read that comes in at time t2, so that read can't proceed immediately. Because that leader knows that it just proposed a write at time t1, and so it can't serve the read until after that write at t1 has either run through the process and been completed, or failed and been aborted.
Yeah. So this is pretty edge casey, but what happens if I try to read a value at a certain time, and I find out that time has been garbage collected away? Then
that would just be an error, and so each range knows what's the most recent data that's been garbage collected, and it won't let you read any further back than that.
Okay, so prior to Spanner, there was a Google technology developed called BigTable, and the authors of Spanner commented that Engineers who used BigTable sometimes complained that it was difficult to use. What were the usability problems of BigTable, and how did Spanner improve upon them?
So the fundamental problem with BigTable was that it was not transactional and it was eventually consistent. So essentially, the problems of BigTable are the same as the problems of most NoSQL databases today, which means that your data you have to be very careful in the way you handle your data, because you may be seeing an inconsistent view of your data at any given time. You may be seeing you may see an index pointer before the record it's supposed to point to, or vice versa. And you may see, two different indexes that are mutually inconsistent with each other. For example, BigTable didn't even have built-in support for indexing. You had to do all of that by hand. And so you could build systems on BigTable as long as you could, tolerate a certain amount of inconsistency. And a lot of applications can, if you're it doesn't really matter if if a like takes a few seconds to show up, or if your like count is off on a photo when you view it. But for other things, like if you have a comment thread where comments are showing up out of order, that can make things very hard to follow. And so, depending on your application's tolerance for inconsistent data, it was either it was varying degrees of difficulty to try and fit that into the more limited capabilities of BigTable.
We started out this conversation talking about the high-level design principles of CockroachDB, and we've touched on some of those. We've delved down into the depths of the engineering aspects. What are the aspects, the high-level design principles of CockroachDB that we haven't really touched on? Survivability, perhaps?
Survivability is closely linked to consistency in my view. Survivability is certainly an important principle. I mean, it's so important that it's where the name of the database comes from. It's a database that is as difficult to kill as a cockroach. And so what this means is that because your data is fully and consistently replicated across at least three copies of everything, then that you can lose a machine and everything just transparently shifts the work to another replica that's still up. When a replica group loses a member, then the two surviving members of that group will run an election amongst themselves. They'll be able to pick up right where the failed node left off, because everything is consistently replicated, and then the repair process will kick in and say, okay, this group only has 2 live replicas. I need to find a third one, and then it uses the same mechanism as rebalancing to reassign that data to a new host.
Okay, perfect. And so at a product level, CockroachDB claims to offer the strongest survivability story in the industry. Is there an edge that CockroachDB has against similar systems from, Amazon or Google or Microsoft?
So when you're comparing it to the services that are provided by the cloud providers like Amazon's DynamoDB or RDS or Google's counterparts with their cloud data store and their cloud managed SQL offerings, but it depends. The level of survivability that you get with these products varies from product to product. For example, I think DynamoDB, until recently at least, couldn't do cross-region replication. You had cross-availability zone replication, but it was still tied within a single region. With CockroachDB, you can configure your replicas however you like. You can spread them out around the globe. we don't currently perform very well in that case if your replicas are too far apart, just because we're not as efficient as we could be in terms of minimizing unnecessary round trips between the replicas. But it will work and stay consistent no matter what. One big advantage that we have in comparison to any offerings from the big cloud providers themselves is that we're sort of neutral in terms of hosting situations, and so you can take you can start out with CockroachDB on EC2 and then migrate from there to CockroachDB on Google Cloud. You can actually run this concurrently. You can replicate from one cloud into another cloud, or have a third replica in your own physical data center. And so you have flexibility with CockroachDB that you don't always get with a cloud provider's managed solution.
So Google is working to build its own cloud platform with externalized versions of internal services, like things that they've written papers on, like TensorFlow and BigTable. How does CockroachDB differentiate from what Google might be able to do if they built an external implementation of Spanner?
So I think the biggest thing is just what I was just saying about avoiding lock-in. With CockroachDB, you're not tied to Google's hosting. You can take your data and replicate it out of Google's cloud and into another, and so that gives you gives you a lot of flexibility. It gives you leverage for finding the best prices. The other big advantage that we have is that because we're open source, we can CockroachDB can run everywhere from your laptop on up to a huge cloud deployment, and so you're running exactly the same database in your development environment as you are in your production deployment, and so that's something that you're unlikely to get from Google. They would have to build a separate local development version, as they've done with their App Engine data store. But then you're developing against something that's not quite the same as what you would see in production.
Right. So their incentive is always going to be to make some sort of black box PaaS thing that works on top of the Google Compute Cloud, but does not run on your own laptop where you're not paying for Google infrastructure prices.
Right.
Okay. Very interesting. Okay. Well, I'd love to begin to wrap up. What are you working on now at Cockroach, and what's in the future?
So as we're recording this, we actually just released our first beta version last week. So we hit beta 1, which is still is still a fairly early stage of development for a database. People are rightly very cautious and conservative in deploying new database technologies. So if you're so a first beta of a database is definitely for adventurous early adopters. But this does mean that we've reached a point where it's more or less usable. We're not going to make any more backwards incompatible changes that'll break your application if you start developing against it. And so this is we've kind of moved from the initial development of the core functionality and features into a stabilization and performance phase of development. And so right now our efforts are all on ensuring that the system works and performs well under load, and degrades gracefully when overloaded. It doesn't just run out of memory and die and things like that. So our focus right now is on stability and reliability, and getting from beta to the kind of 1.0 release that you'll be able to trust your live data with.
Well, that sounds like a great place to close off. Ben, thanks for coming out of Software Engineering Daily. CockroachDB is a really cool project, and You have done a great job of explaining the distributed systems concepts, the distributed database concepts that can sometimes be difficult to discuss over pure audio. So thank you.
Yeah, thanks for having me. It's been fun.